Hello guys, welcome back. In the first part of this video, we have introduced what are bitwise operators and we have discussed bitwise and bitwise or as well as bitwise XOR. If you haven't watched it yet, I recommend checking it out first. So now let's continue with the remaining bitwise operators. So we have something called left shift. The name itself says we need to shift the bits towards left. So but nothing but left shift is multiplying with the base. As we are working on binary, so in binary, the base would be 2. Let's take some example. 5 left shift 3. So here 3 is nothing but the number of times you are supposed to perform the left shift operation. So as I told, left shift is nothing but multiply with the base. So here we multiply by base 2. So now let's take 5 multiplied by 2, multiplied by 2, multiplied by 2. So like 5 to is 10, 10 to is 20, and 20 to is 40. So the answer would be 40. Let's convert the value of 5 into binary. It's 101. Let's try to shift these bits 101 one by one towards left side. So shifting 101 towards left side, so we get the right side gap. So there we'll try to accommodate the value 0. So once again, if you shift all these 4 bits, again you add one more 0 at the last. Again, if you shift all these 5 bits, you add one more 0 at the last. Now if you observe, so this is at the place of 2 power 5, 2 power 0, 2 power 1, 2 power 2, 2 power 3 is 8, 2 power 4 is 0, 2 power 5 is 32. So 32 plus 8, we are getting the value 40. So this is how left shift works. Now let's check with right shift. So right shift is quite opposite to left shift. So we divide with the base. And of course, in binary, we are working on base 2. So let's take the same value 40. So 40 right shift 4. So nothing but here you are supposed to divide the value 40 by the base 2 4 times. So 40 by 2 it's 20, 20 by 2 it's 10, 10 by 2 it's 5, 5 by 2 it's 2. So let's take the value of 40 in binary. As we have already have the value 101,000 on the left side, let's pick the same value. So if I try to shift these bits towards right, the rightmost bit will be lost. So let's remove the rightmost bit. Again, let's do it one more. So now this second rightmost bit will be removed, and next one more 0 is removed, and again if you shift for the last time, the last bit 1 is removed. Now the leftover bits are 1 0. So 1 0 meaning in decimal, if you convert that to, it's 2. So this is how left shift as well as right shift works. So basically, if you want to remove the last digit from any number, you are supposed to do right shift with that respect to base. As we are working on binary, so we are dividing by 2. So now let's work on decimal base. So we have the value 1, 2, 3, 4, 5. So if I divide by 10, you get the value 1, 2, 3, 4. So again, if you divide 1, 2, 3, 4 by 10, you get the value 1, 2, 3. Again, if you divide the value 1, 2, 3 by 10, you get the value 1, 2. Similarly, like 1, 2 by 10, you get the value 1. Next, 1 by 10, you get the value 0. So this is how the operation works. So the same logic we might be using to find number of digits in our upcoming video series. So these are something about left shift as well as right shift. Now let's go to the last bitwise operator, which is negation. So when I say negation, right. So here let me consider two parts. The first part I would say in binary. So when I say in binary, negation of 10100, so we would get all the bits to be inverted. If it is 1, you get the output to 0. If it is 0, 1. So this is the value of negation in binary. But normally when we try to do negation, we will be working on decimal system. Let's also check what is the value of negation in decimal base. So negation of, maybe let's take some number. So basically negation of any number in decimal base, we would get the value to minus of number plus 1. Right. So if I take some example like negation of 5, so the answer would be minus 6. So minus of 5 plus 1, the answer would be minus 6. If I take negation of 20, the answer would be minus 21. Similarly, if I do it vice versa, so let's check for that even. So if I do negation of minus 6, So you get the value to minus of minus 6 plus 1. So which is minus 5 inside the bracket. So minus into minus, you get the value to plus. So now negation of minus 6, you get the answer to 5. Similarly, negation of minus 21, you get the answer to 20. So this is regarding bitwise negation. Let's also observe the same outputs in our ideally. So let's take 5, left shift 3. So the answer is 40. So let's do 40 right shift 4 times. The answer is 2. Similarly, as I told 1, 2, 3, 4, 5, if you divide by 10, so the last bit would be removed. Similarly, if you want to extract the last bit from that, so you do modulus with that respective base. So if I do 1, 2, 3, 4, 5 modulus 10, you get the last value from it. Similarly, if I go over here, let's take the value 5. So if I take this value 5, so if I want to get the last bit out of it, I'll be doing modulus 2. Because in binary, if you do modulus 2, you get the value to that respect to 1. So if you do 5 modulus 2, the answer would be 1. So this is the value. So 5 modulus 2, the answer is 1. So you get the last bit over here. So this value, which is we are seeing, it is present in binary. So, but we are doing it on decimal. We are getting the value of that respect to bit in binary only. So as here also, if you observe, you are doing it in decimal base. That's the reason you're getting the last value to 5. So if I do 1, 2, 3, 4 modulus 10, then you would get the value to 4. So let's similarly see negation. So negation of 5 is minus 6. Similarly, negation of 20 is minus 21. So negation of minus 6 would be 5. Negation of minus 21 is 20. So that's all for this video, guys. See you guys in the next one.